Right, good morning, everyone. So people who were here yesterday, I did an introduction about myself yesterday. So I'm Managing Director at Valid. I've been in the industry for 33 years-ish, and I'm going to talk today about ISO 14644 Part 4. I was a technical expert on the update to that standard, and I'm going to feed back the information. I've delivered this presentation similar to this before. I've got some bits I want to concentrate on today, so I may bounce through a couple of slides a bit quickly, just so that we can get, I don't want to miss out the opportunity to get to some of the important stuff, because we've got quite a tight time slot. So the standard itself was a 2001 standard, and so periodically, every 5 years, all standards come up for potential review. So the discussion is made about whether the standard needs to be updated or not. It's voted upon and decided whether it needs to be updated. So it was voted that it needed an update. So a working group's put together, and they have a kind of a very loose outside remit of what wanted to happen. So what I wanted to do was address misleading and out-of-date information. So it's felt that 2001 had some information that was 20 years old. Technology had changed, people's thoughts had changed, etc., and it was felt that some information was out of date and a bit misleading. We wanted to acknowledge that there had been improvements in cleanroom design over 20 years. As I said yesterday, cleanroom technology doesn't move super quick, but in 20 years there had been some changes and some improvements in that, and we wanted to reflect that in the update to the standard. We needed to consider other contaminants. So since 2001, there's been other standards within the ISO 14644 family that have dealt with other contaminants. So chemicals in air, chemicals on surfaces, and particles on surfaces have all got their own standards now. And we needed to make sure that the design and construction considered that in its update. And we wanted to improve its reviewability. I don't know how many people have read the 2001 version. It's quite a heavy read. It's quite a tough read. I wouldn't say it was super popular. So we wanted to improve its readability. So we started in 2015. There was a committee. We did a couple of committee drafts that go out for P member votes. Then we had a draft international standard came out, which people commented on, and then an FDIS. And the current document was issued at the very end of November 2022. So it did come out quite quietly. I don't think even I realised for about a week that it was out. It bypassed pretty much all of us and slipped out. So, but it's out. It's out to be able to purchase. So go to BSI and buy it. So here we go. So the main changes. So we wanted to update the sequencing of the clauses within the standards. We wanted to do it as a logical timeline. The standard's written as design, construction, startup. So we wanted the document to read like that. As it currently was, it didn't really read in that kind of manner. It was very hickledy-pickledy. So there's a bit of restructuring that we did to align that. And in the same bit, you have normative section and you have informative section in standards. So the normative sections are your must-dos. The informative sections is your we'd like you to do's. It's the recommendations. We wanted to align them because they were very misaligned. So the section regarding requirements. The talk before spoke about user requirement specifications. We wanted to expand on that within the document to give a bit more information, the kind of information that should be provided as requirements when you're designing the clean room. So that section got expanded. We felt that the design section was really brief, really short, and we wanted to expand on that. Design could be quite complex. It can have a number of stages, and the standard didn't really say that very well, so that's been changed to reflect that. As I said earlier, other cleanliness attributes, we had to consider that. And also energy management. I mean, it's been in the last 5 years, it's been a huge change in people's concepts of energy management. There's been Part 16, ISO 14644 Part 16 is energy management for clean rooms. And we needed to consider that. That wasn't considered at all in the previous standard. So we needed to consider and or at least point people towards that when they're using the standard. And then the bit which I want to talk more about is removing misleading information, misleading and out-of-date information. And the big one to talk about is clean room air change rates. The industry in itself, the whole industry, all been done. Well, we need to know what the clean room air change rate. What do we design the clean room air change rate to be? Hopefully, I'll be able to give you a bit more information on that. You may go away more confused than you started with, but just specifying an air change rate is not the answer. And there was information around clean build protocols. So a really important part of construction is when you're constructing a clean room facility, you implement a clean build protocol, which you put measures in place to improve and increasing measures of control to limit the contamination that's being introduced to the clean room while you're building it. So information on that has been expanded within the standard as well. So if we look at what the current standard looked like you've got design, construction, and startup, and a requirements at the section. You had a normative section that looked like this, and then that had a bunch of annexes that was your informative section. So if you had requirements and you wanted to look to see where the information was in the document, you went to the normative section, and then you went all over here to try and find information in the informative section. Same with design. You looked in there in the normative, and then it was all over, information was dotted all over the place in the standard. So it made it quite a complicated document to read and go through the construction, and startup was the same. So we had a real kind of messy sort of approach. So the first thing we did was just straighten that all out. So we straightened the standard out so it looks like that. So you've got requirements, you go to the normative section of requirements, and there's a normative section which is guidance on, an informative section, sorry, which is guidance on requirements. And that followed through design, construction, and startup. So that was a big restructure that we did to the document to try and make it easier to read. So I'm going to whip through some of the changes now that happened on the document. So when we look at requirements, we've got three normative parts there, and then an annex on the requirements. So within the requirements, we wanted to make sure that we covered regulatory requirements, so people understand what standards were applicable. We took personnel, product movement need to be identified in requirements, what monitoring you wanted, if you wanted to turn down the facility at all, you wanted to do anything, any of the energy efficiency measures for it, how you wanted it to perform, any acceptance criteria you want to lay down, if you had the other cleanliness attributes, if chemical contamination was an issue for you. These sort of things needed to be things you need to think about and put into your requirements. And then there was another section so outside of the cleanroom requirements, which lists other things that you might considering your project budget, looking at time schedules, competencies of people who are doing the work. That was mentioned earlier about, is your cleanroom contractor experienced in delivering the project that you want? It's really, really important. I've seen a number of projects where the people building the cleanroom have never built a cleanroom before. And it brings interesting challenges that you don't think about. Things you think, being in the cleanroom industry, you think it's just so straightforward, doesn't come across to people that have never been in the cleanroom industry and are trying to build a cleanroom, and it creates real challenges. So the way the requirements section works now, it kind of lists out a number of things to think about, things to consider when you're putting your requirements together. And in the annex of that, it gives some information on the mechanisms of contamination. So how could as you're looking to put your requirements together, you go to the annex and look about how the mechanisms of contamination, get an understanding of, well, how does contamination end up in my clean room and how does it move around in my clean room? And then how we minimize that contamination. The real obvious things: minimize the contamination that gets in the room, minimize the contamination you generate in the room, and the contamination you do generate, get rid of it quickly. And that's kind of like the focus on that. Each of the sections has a requirements checklist, a checklist. So this section is requirements, it has a requirements checklist. That's like a little ready, reckon, a tick box at the end of each of the annexes that you can use to say, have I considered, is this relevant? It was in the old standard, but they were all together in one section. It's all been moved to each individual section. It's okay, that bit. Room for improvement, I would say, would be my opinion on that one. I think I'd like to have seen that a little bit more focus put on that. But it's useful. It's useful. They're useful. I just think they could be a bit better. So move now on to the design section. So the design, what we've identified now is three stages. So we knew that there was a concept design stage. So this is the very early bit. It's what we used to call back of the fag packet type stuff, where you're doing adjacencies, you're getting your ideas together and coming up with a basic concept design. I think if you're familiar with REBA stages, it's probably REBA stage 2-ish type of comparison. And so you put together basic layouts, you do some basic calculations on stuff and might put some very sort of outline bits together, what rooms need to be next to each other for flows to work, that kind of thing. And that's the concept design. Also as well, the standard identifies that for some projects, depending on the size of the project, you may not have 3 clear stages of design. You know, a simple, straightforward project might just be one stage. Everyone sits around a table, discusses the design develops, it's done in one go. But it's kind of saying that really there are structurally kind of 3 stages that you would look at. So after the concept design, you'd move on to the basic design. So basic design then starts to get a bit more detail. You start to put your flows in there. You look at calculating, getting schematics produced, doing all your design calculations, and you're coming up with a scheme which you think is going to be how you're going to go forward. So you have a lot of information goes into that basic design stage. And then the final bit that you're looking at will be the detailed design, and that's really getting it ready for construction. So you get all your drawings get finalised and approved, all the specifications get put together, and you're ready to go into construction. At each of these stages, you should do a review. I won't use the word qualification. ISO standards aren't just specific for our regulatory environments, they're across all industries. So, but you should do a review at each stage of design. So you look back and go, okay, we've developed this design. Have we moved away from those requirements we spent all that time getting right to say what we wanted? So you go back at all those stages and go, yeah, are we still in line with that? If we're not, there may be a good reason for it, and you just document what that reason is, that we know we've moved away from it because we've got a better solution somewhere else. And there's a section within the design which is on change management. It talks about just controlling and approving changes, so the change control that we would see in our pharma world. So looking onto the annex now, so the annex for design, you've got a number of elements in here within this section, and I'm going to concentrate really on contamination controls concepts and air volume flow rate calculations. So there are all these sections within the annex, but I'll concentrate on those two. Contamination control strategy gets talked about all the time, and it's the big buzzword since it appeared 1,000 times in the new Annex 1. But I'm going to so just briefly on contamination control strategy, there are kind of three main controls. You've got engineering controls, you've got personnel material controls, and then you've got your cleaning and disinfection. They're the three main controls. Everything really kind of pretty much falls under those three subgroups when you're looking at contamination control. And then there's some information within the standard about putting an effective contamination control strategy together. Remember, it's not a pharma document, it is a worldwide document. So there may be other things and other nuances with regard to GMP environments that the ISO standard won't cover in that detail. It can't. It needs to be non-industry specific. So I'll go on to the contamination controls concept. So the first part of the contamination controls concept in the standard is about zoning. This is the box in the box scenario. So it's about where you have a core area in the middle where your process goes on, and then you have boxes of protection, usually with a pressure cascade, typically decreasing pressures as you go out. So you have your flow materials coming in, the flow of finished product going out, you have a route for waste, and you have a route for personnel coming in and a route for personnel going out. And sometimes that route for personnel in and out might be separate, so it might be unidirectional flow of personnel. That's an ideal scenario, but often constrictions on space and size, people use changing rooms as in and out changing rooms. So that's the first thing, zoning. So the first part of a contamination control is to zone those areas off, provide that protection. Know that that's the most critical area, less critical, and you protect that with a pressure regime. So that zoning is the first contamination control concept. Then we have segregation. So in addition to that, the way that you would separate, you deal with contamination control can be by segregation. And there are three defined in the standard, three defined methods what this is done. So the first one is a physical barrier. It says physical barrier with leakage because everything leaks to a degree. But for example, would be an isolator, a solid wall is effectively a physical barrier. What might be considered B, was the second one, would be a physical barrier with a known leakage or overflow. So I've just shown a picture below with a pressure stabilizer there as an example of where you've got a physical barrier, but you've got a known flow of air providing that protection. And then the third is an aerodynamic. So you don't really have any true physical barrier. It's done by airflow. Airflow creates your barrier and creates your segregation between contamination and the clean environment. So there used to be airflow concepts. This is what was in the old standard, the 2001 version. We had all these pictures in there, which some were a little bit confusing, some seemed a little bit pointless. So we just got rid of them. So they all came out. And airflow concepts was replaced by effectively two simple concepts. So your cleanroom will either use unidirectional airflow as its means of displacing contamination, or it will use a non-unidirectional, or what we hear as turbulent airflow, which will be to dilute the contamination. So there's two different things. So the unidirectional flow pushes the piston effect, pushes the contamination away. Any contamination gets generated, gets pushed away from the critical area. With non-unidirectional, it dilutes it. So that your clean air comes into the room, it dilutes that contamination to a concentration that's acceptable to you, and then that disappears out through the system. You could have a mixture of the two in a facility, of course, but essentially, when you break it down, It's either unidirectional or non-unidirectional. That's just a quick CFD kind of example of there you've got unidirectional airflow in the middle, pushing the contamination away, and you've got a couple of air intakes at a high level there, creating turbulent airflow, which is just diluting the air. And there's two different concepts shown in that area there. So that's airflow concept, simplified and understanding what you do. So generally speaking, the tighter your requirements are, so the cleaner you want your environment, the more you lean towards unidirectional flow, and the less clean you need your environment, then non-unidirectional works well. Here's an example of some concepts in practice. So here's a layout of a facility. The areas identified at A are all isolators. They're all pharmaceutical isolators. And they're using the physical barrier with leakage, because isolators do leak. But they're using the physical barrier concept, and they're using displacement unidirectional airflow. And that's all of those great, and they're grade A, those environments. So grade A environments are using unidirectional flow. That's in the revised Annex 1. They're kind of almost insisting upon unidirectional flow in grade A environments. That's certainly a big point. If you're not going to use it, you need to have a really good reason why you're not using it. And then the grade B areas, these were designed to be grade B. They're not operated at grade B on this facility. They were designed to grade B, and they use dilution. So they use dilution and the physical barrier with leakage. So that's how the concept is for that, for contamination control there. So yeah, and as we go out to the lower grade areas, the C and D areas, the outside areas, there's changing room at the top right-hand corner there. They're using dilution and just overpressure. So that suites a traditional cascade of pressure from the cleanest air grade B areas throughout to the grade D areas and to outside. So that's an idea of them together. So the bit I wanted to talk about, and I'm going to take a drink first. So historically, airflow rate calculations historically. So for unidirectional flow, when we wanted to know the air volume flow rate, it was the velocity by the area of the intake of the supply, and that gave us the air volume flow rate. Non-unidirectional airflow, people said, well, it's an air change rate, so we need to take the airflow rate divided by the room volume. That gives us the air change rate, and the air change rate is what we need to do. So the air change rate is effectively, the airflow rate for a non-unidirectional flow room is the air change rate times the room volume. So everybody talked about air changes, and they still do. I still go to meetings and people say, we need to specify what the air change rate is for this area. As users, as end users, you need to specify in your user requirement spec. And I have to slow people down and say, no, we don't. It's not our job. So the reason for this being is that the airflow rate is the value of the airflow rate is dictated by the room volume and not by contamination levels if you're doing it by air change rate. So if you specify by air change rate, it depends how big the room is as to how much air you need to put in. It doesn't depend on how much contamination is in the room. So surely you need to be thinking about how much contamination is in the room, not just the size of the room dictates how much air you put in it. So I'll go into a bit more detail. So within the new standard, we've got a calculation for a formula for estimating the air volume flow rate you may need for your clean room based on the source strengths within the clean room. So the supply air volume flow rate you need is the source strength. So that's the number of particles being emitted by people or a process or machinery per second. And you divide that by a ventilation effectiveness, which I'll explain in a moment, and the particle concentration limit number that you're looking for, so the classification limit, or a proportion of that limit. If you don't necessarily want to be putting in the maximum level in these calculations, because then you're designing around just being in class. But a particle concentration limit, and that's an equation to use there. You can also, with that, the other thing to think about is that if you've got a device like a unidirectional airflow cabinet or an isolator that's recirculating in the room, that's providing clean air into your room. So if you're looking for the air volume flow rate you need for cleanliness, well, you can include that value in that. If that's always going to be running all the time, you can include that in your design for cleanliness, for keeping the room clean. But therefore, you can take it away, you can minus it from the value that you're looking to as what your HVAC is going to provide. And then you can also take away elements that deal with particle deposition. There's a little equation there, the VDA, at the end, which is about particles that fall out of the surface. So there's a little adjustment you can make, but I'm going to talk about just the simple bit, so that the orangey brown bit is the bit I'm going to talk about. We'll leave the slightly more complicated one, but just in the simple one, we'll talk about that. So ventilation effectiveness, this is this epsilon that appears underneath the source strength part of the formula. So the ACE index is effectively the effectiveness of your clean room. So all clean rooms will have, if it's a turbulent flow, you want it to have the best ventilation effectiveness that you can get. So what you want is, ideally, all the air to get to all parts of the room at the same rate. That's the idea. So nice, if you've got a situation where you've got one filter sitting in the ceiling over this room, one filter sitting over here, you're providing a ton of air over here, the extract's over there, the air wanders over there, not much goes over there, very poor ventilation effectiveness. So good even distribution of supply, good even distribution of extract. And the epsilon is a factor that you put into this, which is around, it's effectively the local air change rate versus an overall air change rate. So what's my air change rate where I'm standing here compared to what the overall air change rate is for the whole room? And that's how you have a ventilation effectiveness factor. And typically, I'm going to use a value of 0.7 for this. With studies that have been done, you get quite a variation, but when you try and average out on a well-designed facility, a value of 0.7 is probably quite good to put into there. So I'm going to use 0.7 in some calculations later. But that ACE index, which is the ventilation effectiveness, the local air change rate versus the overall air change rate, it's actually the same as saying the local recovery rate by the total recovery rate. So the recovery rate at a particular location compared to the average recovery rate for a room is the same as saying the local air change rate against the overall air change rate. So recovery rate. So this is important. In GMP, it's important. It talks about clean-up time and after completion of operations. That used to be 15 to 20 minutes. It's now less than 20 minutes in the revised Annex 1. So here's an example of a recovery rate. So what we've done here, released particles at that first minute. Seen that considerable, so on that vertical axis, we've got particles at 0.5 micron per cubic meter. So we've got an introduction of particles. The contamination in the room goes up really high. You have a mixing period. That's where that contamination is mixing with all of the room. And then you have a decay. So and on a logarithmic graph, it's an exponential decay, but it becomes a straight line on a log graph like this. That's the decay period. So that's the period you're interested in as what would be considered your decay or cleanup time. Once you start to get towards the end of it, you can see at the end of the curve, it starts to bend. That's because you're getting the influence of the natural background in the room. So when you're looking at recovery rate graphs, it's not from the very, very start to the very end. That's not your recovery rate. It's the straight line section on the graph is the easiest way to put it when you're using a log graph. Here's an example. With perfect mixing, so that's where that ventilation effectiveness I talked about being 1, not 0.7. With perfect mixing, here's an idea of what your air change rates will give you for recovery. And this is where air change rates are relevant. They're relevant for recovery. So when you have an introduction of contamination, it's about how quickly that recovers. Air change rates do that. Air change rates absolutely provide that. So when you look at this with perfect mixing, if you look at the green one, which is 80 air changes, you've pretty much got rid of most of your particles in 3 or 4 minutes. At 20 air changes, you're looking probably at 14, 15, 16 minutes before you've got rid of those particles. So 99% of particles, so kind of 100 to 1 type cleanup, with 20 air changes is going to take you 14 minutes. 40 air changes, 7 minutes, 80 air changes, 3 minutes. Really, really good for cleanup. So really helpful for things like a transfer hatch. So transfer hatch, people have timers put on transfer hatches, the typical 2-minute rule of thumb. Well, you're probably looking at around 100 air changes if you want everything to be cleared in 2 minutes. From that point, you've opened it from a dirty side, you've put items in it, you've closed it, leave that for 2 minutes at 100 air changes, and you know you're going to have cleared that contamination away. All the airborne contamination is cleared away. So for that point, air change rates are important. So air change rates are necessary for recovery, but the air change rate value is not what dictates how clean your room's going to be. So here's an example. So if you wanted a 15, for grade B area, 18.4 air changes with perfect mixing, will give you a cleanup of 15 minutes. Sorry, when I wrote this slide, Annex 1 wasn't out, it was 15 to 20. Now it says less than 20, but for 15 minutes, it's 18. For grade C, it's 9.2 air changes. But again, that's just for cleanup. So historic air changes. So the old standard, which is one of the bits we wanted to move, had this table in it. And if you look at this table, if we look at ISO class 7, the second to bottom one there, so your air changes should be 30 to 70. That's not very helpful, really. If you're designing a facility, if I design it at 30 or 70, there's a massive change in the size of my system. What determines where I need to be? Do I just go with 45 You go like that and go, yeah, we'll go 45 and we'll be safe. So it wasn't particularly helpful guidance. What people didn't realise on this is that those air change rates are related to a ceiling height of 3 metres. So if you didn't have a ceiling height of 3 metres, you need to think about it differently. And we've got some guidance. So ISPI gives us a guide, talks about ISO 7 areas, 40 to 60, ISO 820 to 40. Co-ops, if people are in the NHS, you've got a minimum 30 for ISO 7, minimum 20 as air change rate guides. But that's really, that's only talking about recovery. It's not talking about what you need for your area to remain clean. So we got rid of that in the standard. It went completely. So we took that table out. So that table doesn't exist anymore. And that evaluation and calculation is what comes in. So using source strengths is what comes in. I'll try and give you a practical example of why specifying air change rates can be misleading. So this is what the standard said, the old standard said. I've got an ISO 7 room, air change is 30 to 70 an hour. So I've got my clean room. I'm going to have 10 people in my clean room. It's going to be an ISO 7 clean room. I'm going to have 10 people in there. It's a 3 metre high ceiling. It's 8 metres by 8 metres. So at 30 air changes an hour, I need 1.6 metres cubed per second coming from my air system. At 70, I need 3.7. That's another air handling unit on top of the one I've got. So where do I go with that? But 1.6 for 30. If I start to look at that, the formula, so I've taken a typical, so the 35,500 particles per second came from a study done by Bill White in a body box. So they had about 50-odd people they put into a body box and kind of measured particles. They're just wearing gowns in this example. I'm not saying this is the solution for an ISO 7 area. I'm just giving you an example of how it can go wrong. So if I've got, using that calculation, using that formula, losing a ventilation effectiveness, my concentration limit for ISO 7 at 352,000 particles, I've got required airflow of 1.441. That's a bit less than they're specifying. That's less than the 30 air changes. That will give me concentration at my limit. But I want to be less than that, so I'll probably have a bit more. So you go, okay, well that seems a fairly reasonable kind of number. But what happens, all of a sudden, my process has changed. I don't need a 3 metre ceiling anymore. I can have a 2.4 metre ceiling. That big bit of equipment I was going to put in the suite has been redesigned. It's much shorter now. So my room volume goes down. My room volume goes down. My air changes go down. If I'm going by design, my air change stays the same. My air volume reduces. Because my room's got smaller, my 30 air changes need less air to get there. So I only need 1.282 metres cubed per second now. But when I look over on the other side, I need 1.441 to keep the concentration level where it needs to be. So all of a sudden, I've designed a room at 30 air changes. Later in the design, someone said, oh, we can drop the ceiling. And someone's gone back and gone, oh, we can reduce the air volume. But my room's dirtier now, and my room might be too dirty. If that's a concept people can understand. So what I'm trying to identify, that's the risk when you just say air change rates. Air change rates is about the size of the room. It's not about the activity that's going on in it. And the air volume flow rate you need in a room, I mean, there's other factors with air volume flow rate, heat gains, pressurization, dealing with extract, etc. But this is another factor you need to think about, and a really important one. It can also work the other way. You could also find that if this room isn't occupied by 10 people, I mean, this equation's simplified. I've not allowed for any machinery sources of contamination from machinery. I've assumed HEPA filters, no leakage from filters. But if you think, if there was only 2 or 3 people working in that clean room, that required air volume flow rate to get that concentration would drop considerably. And there's a talk later today. Keith from EECO2 is doing a talk on a dynamically controlled clean room that they've got. Some really interesting information to support what we're saying here. So definitely listen to that talk later today. Yeah, so that gives you an idea. And then just as another example, if I put more people in that room, so I decide, oh, my process, I need more people to deliver that process, or another form of contamination, process equipment. So my source strength goes up, my required flow rate goes up to 2.1. Well, 2.1s are well above the 1.6 I had for my 30 air changes. So you can see how I'm not going to use the word irrelevant, although I really want to, how less relevant just specifying air changes is. So that's a big change in the standard, and a big change I want to get across to people. That's a very simplified example just to show you how air changes can be a problem. If you were doing these calculations to calculate what you can do, you're going to apply a lot of other factors. You're not going to set the concentration limit right at the limit. You're going to give yourself some assurance, and you're going to put some buffer in there. But it's a good way of doing it. If you've got an existing clean room, it's a great way to look at the system, and you can get real-time data from what kind of contamination you get. You could turn down your clean rooms, save energy. And that's been one of the guiders in this, has been energy. The cost of energy has become a big factor. So QA don't want you to turn anything down. They want super clean. They want zeros all the time. But energy is knocking at the door saying the cost. We need to be thinking about it. So again, source strength, the known unknown. This is the bit that we want more data on. So there are a couple of studies. I've just mentioned two of ones there that have been done, which give data on source strengths from people in various garments. Because the quality of the garment has an impact as well. So the cleaner the garment, the less particles you emit, then the lower airflow rate you need to get rid of the contamination. There's just a couple there. We do need more data, and it's great. We'd like to see manufacturers of process equipment provide data on what their source strengths are from their equipment, so this can be used. But it'd be good to see more studies and more data. I think some of the filter manufacturers, I think Camfil have got something, I think AF have got some data they've done. I've not seen their study in detail, but there is more data. But what we want now is more data. So what am I doing for time? Yeah? Okay, cool. Oh, cool. So I'll move on a little bit now to other parts of the standard. So I really want to make sure I got that covered, because I think it's a big and important change. And it's kind of a fundamental change in people's thought process about designing clean rooms. So as users, you shouldn't feel the pressure of having to specify what you want your air change rate to be. Unless you've got a recovery requirement. If you've got a recovery rate requirement, then you do need to be saying, we need to meet a recovery of X amount of time. But you shouldn't be saying, I want my room to be 20 air changes. It's not your responsibility. The designers need to do that. So moving on to the construction start of the standard, we've got the general section on it, the normative part, and then we have an informative annex. So within here, we've got the clean build protocol, so a bit more information at clean build protocol. It's about putting a quality plan together, making sure that you segregate materials, that you protect materials, that you start to clean the site, that you various stages you start to put measures in place so that you're not at the very, very end going around clearing up 6 months worth of builder's debris. You've got a process in place that keeps it clean. You control people going in and out. So you have something in your clean room protocol that goes, once we get to this stage, we're controlling who comes in and out of this clean room. We may have a gowning regime for them even though we're not finished. And that's what will go into your clean build protocol. And it talks about verification. So the speech before talked about IQ and OQ and those kind of things. We don't use that terminology in here because it's all industries, so the word qualification gets scared away. So it uses verification. But so you have a construction verification period, which is a bit like your IQ, as people would know. And there's detail there that would happen. You document that. So in the annex. So in the annex on construction, a bit more information on the clean build protocols, information about assembly of stuff, about training of staff, making sure there's competent staff, they understand how they gown, and again, there's more information about verification. And we got a construction checklist. We had a requirements checklist, we had a design checklist, there's a construction checklist in the annex as well, things to think about. That's the construction side. And then the last section is startup. So this isn't startup of production. This isn't you manufacturing product. This is the startup of the clean room. So this is the period where the construction period is finished and effectively everything's done. We're now going to go over and start turning the unit on. This is startup, so it's starting up all of the utilities and all of the services, etc., to get it start up and commission it. So the startup deals with commissioning, then it deals with training and handover. It doesn't deal with production. There's a part 5 of 14644, which is operations. That deals with the period after this. So that's what this part of the standard deals with. So the commissioning period has a setting to work, has functional verification and performance verification. They're what we kind of OQ in our pharma world, but they're separated just slightly by what that means within that section. Then there's a bit about training that needs to be provided and what documentation is handed over at the end. And in the annex, gives you a bit more information on all of those elements. So the commissioning process. So the word commissioning gets used differently, so I just wanted to give you an example here. So there's kind of 3 different ways in which people think about commissioning. So the first one there is commissioning is everything. So inspections, verifications, tests, it's all commissioning. Everything is commissioning. All the adjustments and balancing, it's all considered commissioning. Other people look at commissioning and go, well, you have commissioning as a separate period, which is your testing and adjusting and getting it set up, and then you have your verification as a completely separate function. That tends to be a little bit like what we do in pharma a bit, and probably also the third one where there's a bit of an overlap. So some of the commissioning information becomes part of your verification or your qualification. So those two. But what's important is in 14644 Part 4, it's that one. So when they refer to commissioning, it's everything. So the commissioning period is everything. It's the turning on, adjusting it, setting it up, getting it ready and balanced, recording, taking out those measurements, and then it's also all the verification tests, the filter integrity tests, the pressure tests, particle counts, etc. All come under that. So in 14644, it's one umbrella. It's all under that one umbrella. So I've whipped through a bit. So that's just an excerpt from the introduction of 14644. So that's how there's got a little flow diagram in there that shows you how you keep all the clauses. So that the left-hand side there, all the normative clauses up to 9, isn't it? Yep, clauses 6 to 9, and then where the relevant annexes are. So that's that earlier one when I showed you those arrows, nice and simple. That's what that shows. And that is the end of my speech. So I whipped through, I was very conscious, I wanted to make sure that I got the information out on the air change rate bit because it's the contentious bit. Anyone got any questions?
Hello, hi. It's about the source strength, which I know is the little bit in the ointment here. I know you're saying you want more data, and there's a couple of studies that have been done, a few independent studies. Is there a plan, are we going to get to a point maybe where there's a table that people can refer to so that we've got one definitive? Because otherwise it seems to me that it could be a bit wishy-washy because you could take your own numbers from I don't know where and come up with a number which, you know, won't actually do the job. It just seems like it's the little... I like the idea of it, but that's the weak point as far as I'm concerned. And how do we nail that down?
Exactly. It's what I described the known unknown. It's the bit we just want more data on. So, I mean, I've done a number of things where... so I've got a spreadsheet that I use which takes the data from the study that Bill White did, and I can put what type of gowns, and I can come up and get a feel. And I use that as like a ready reckoner around. Look, if I'm looking at a design, I would look at that. I throw those numbers in and go, okay, I've got some other adjustments and parameters and some confidence values in there, and you can get that. But you're right, and data varies as well. And I use this study because it was 50 odd people. Obviously, you know, the more people you do, the more reliable your study is. But we do need more. The other challenge you've got, these papers aren't easily accessible. So if you want to read that paper, you've got to join that particular society, and then you can get that paper, or you've got to pay for it. And it'll be great, but those people have done a lot of work, and they wanted recognition for it. So then to expect them to just free issue that to the world is probably difficult. But you're right, it would be great if we could have a range to say, right, but there are lots of other variables. You've got all the different types of garments. Maybe garment manufacturers will do something, you know, to help sell their garments. Look how great our garments are. We've done a body box study with X amount of people, and we're showing these amount of particles. I mean, the values I put in there were quite high. They were just a gown, the values from that. When you start to put in really good cleanroom garments, those numbers come down. When those numbers come down, your required airflow rate comes down.
There is the challenge right there. It's a great question, Tony. Everybody should be asking that question. Everybody here operates in some form of a clean room. What is your source strength? Do you know what it is? Is it personnel? Is it machinery? Is it process? What are your starting materials? And we all consider it, but we don't quantify it. So at the moment, every company who's involved with design and or build and construction is going to be making up their own data tables until there's something that's published. Even when there's something published, are you going to trust that and use that as your design and build criteria? And if not, everybody then puts their factors in. So you still end up with an air handling system twice the size of the one you really need. Yeah, so that's where this is coming to meet.
But maybe design evolves in the way that the designers are going to put a cushion in because they're going to be responsible. So they'll put their cushion in, but maybe that's tunable. Maybe the idea of the design now is that can be tunable. So you can design a system that says we can design a system. It's going to have 30,000 meters cubed an hour for the suite, But actually, we can tune that down if we find, as monitoring data comes along, that we can start to tune that down, and we can actually have that control best, and we can reduce it and reduce energy. I mean, turning down airflow rates considerably reduces energy and energy costs. It's massive. So it's a big factor. So Keith's talk later, I know I keep saying about it, it's a really interesting talk to just, blow your mind a little bit about other ways of looking at it.
Yeah, that's the brave world where Keith and David will talk later. It's really where that rubber hits the road. It's where design and construction meets operation, and it's right in the middle. Where is that sweet spot? And they'll show you some quite radical changes based on energy considerations without compromising quality. And that's really where the conversation has to be had. So a new standard, 5 months, 6 months old now. It's really contesting what we've been doing for the last 20 years. And that was a really profound statement saying, no longer just be out there saying, I need 20 air changes, I need 40 air changes. It's not about the air changes.
And I think just answering further, Tony, on your question, I think at this stage, as a designer, I would go through the normal parameters. Can I deal with the heat? Can I deal with the pressurisation? Can I deal with all the other losses? Then throw that factor in as well. Do you know what? If I use this data, am I close? Am I near? If all of a sudden you're coming up with an airflow rate that's 20 times more than you need, or less is the more scary one, actually you need more, then you can make that kind of a judgment and discussion. And hopefully, if we shout about it enough, more information will get to market, more information will get out, and we can start to consider it. But I think what's important is don't ignore it. Don't ignore it. And get the pressure off, stop putting the pressure on the users to tell you what air change rates they want, because it's the designer's responsibility.
Would anybody else like to put a question to Steve? Any other comments? All right, you're free.
Excellent. Thank
you,
you,
Steve.
Thank you.
Well done.